Okay, so we have another problem here that deals with a collision between a block here moving to the left with V0 and a block here attached to a spring where this point here is 0. It's important to note the starting values. So the spring is nonlinear and exerts a force here. This force equation is probably going to be useful later. You might have to differentiate or integrate depending on what we're talking about. Probably integrate. So it's good to note that it is a nonlinear function. B is a positive constant and x is displacement. Block of 3m is moving to the left, and so before they collide, and we noticed that they haven't told us there's friction. In fact, they've said it's frictionless. That we have a free body diagram to draw, or a pair of free body diagrams. So we know that up we have a normal force, and we'll say this of block 2. It's a different value than the one on block to the left. And we have a force down of 3 mg. That's my force of gravity. Then here, I have a force down of 2 mg, Fg1, and maybe this is Fg2. And going up, I have Fn of the first object. So these are some values that I want to keep track of in the future. You should label them with values if you can, just on the off chance that your diagram is not well drawn. So this is equivalent to about 2 points on the AP exam, and it's an easy 2 points, so please take advantage of that. So they collide and stick to each other, and we're trying to find 3 things. The expression for the speed of the blocks immediately after the collision, the expression of the kinetic energy immediately after the collision, and deriving an expression for the maximum distance that the spring is compressed. So this might involve conservation of momentum. This takes that value from there and is just a kinetic energy calculation. And then finally, well, maximum distance that a spring is compressed, that's something that we might want to calculate as well from the spring equation that was given above. The spring equation being negative beta x to the third. And that is the force equation. Now, it's potential that we might want to find the kinetic energy equation. So keep that in mind there. Okay, so let's move to the next value. So for B, move to the next screen. Let's see, we have conservation of momentum. Just saying that will get you the point here. Well, we know that the momentum initial is going to be solely from the first object because the 2m block is moving at speed 0. So we have 3m times v1 plus 2m times 0 equals the combined mass times the final speed. Well, in this case, we have 3m v1 equals 5m vf. Divide each side by 5m. And we get 3/5 v1 is vf. Okay, that's a pretty useful value. In fact, I believe this is actually labeled v0. So let's change this notation to v0 just for clarity. And that is going to solve part B. Just a simple inelastic equation there. Now the question is, what's the kinetic energy of a two-block system immediately after the collision? Well, we know the speed of the two-block system, so the kinetic energy of the two-block system, which has to be in terms of V0, can be determined by C that equation. So how do we plug things into that equation? Well, we get 1/2 of the combined mass, 5m, times 3/5 V0 squared, and we'll get 5/2 m times 9/25 V0 squared, and this would be 45/50 mv0 squared, which is 9/10 mv0 squared. Is the kinetic energy. So finally, for D, well, if we know the kinetic energy, and we know the force equation, well, first we should find the kinetic energy of the spring, or the not kinetic energy, in fact, the potential energy of the spring, which we can do by taking the negative integral of the force equation. Potential energy is the negative integral of force, and we want to know in terms of D, so we want to know from 0 to D what the value is. So let's do this integral. So we have the negative integral from 0 to distance of negative beta x to the third. Well, we can take the negative beta out, and we get beta times 0 to d of x to the third. Well, that's just x to the fourth over 4, evaluated from 0 to d, times beta. So plugging in 0 gets us 0, so this is just beta d to the fourth over 4 is equal to 9/10 mv0 squared. So this is the potential energy of the spring has to equal the kinetic energy of the object for maximum compression. Okay, and so if we want to resolve this, well, we have to isolate the d value here, which means we have to multiply both sides by 4. I'm going to move this over here. So we get 36 over 10 mv0 squared over beta, so 10 beta. And then we take the fourth root of that, and that is my distance. This can be simplified to 18 over 5. So this could be termed the fourth root of 18 over 5 beta mv0 squared. And that would be sufficient to answer the question. Either one of these should be fine. So let's move on to part E. In which direction is the net force, if any, on block of mass 2m when the spring is at maximum compression? So when the spring is at maximum compression, It's at maximum compression here. This is 0 somewhere over here. This is position D. And we want to know which direction is the net force on mass 2m. Well, are we getting a force from 3m? Not really at that point. We're getting a net force that's pushing back. And that is because what's about to happen is the spring is about to release its energy. Now, if there were an equilibrium position, well, we'd be able to see that that would probably be around 0 when the spring is at rest. If we were in a vertical situation, it might be different. But in this case, we have a net force to the right, and which describes the magnitude of the net force on each of the two blocks when the spring is at maximum compression. Well, obviously, this is the situation where we have 2m here, 3m here. They run away with the same acceleration, and we have the spring force pushing here. But if the force is on both of these objects, then we have the F equals 5m A. So F over 5m equals A. But the A on this has to be the same as the A on this, which has to be the same as the A on this. So the net force is actually going to be 3ma on this object and 2ma on this object. So actually, what we get is that the net force is greater on the block of 3m.